Welcome to another video session. In this video, we are going to discuss another worked example of body part. Okay, so the control system as g of s into h of s is equal to 25 into s plus 4 divided by s into s plus 1 into s plus 10. Sketch body plot. Determine gain margin, phase margin, and stability of the system. Okay, so coming to solution. So okay. First step is identify whether it is standard time constant form or not. And so this one is not standard time constant form. Okay. So bring it to standard time constant. Okay. So that is g of s into h of s is equal to 25 1 plus s standard time constant form. So 1 plus s by 4 divided by s into 1 plus s into 10 into 1 plus s by 10. If we simplify this, okay, so if we simplify this, g of s into h of s is equal to 10 into 1 plus s by 4 divided by s into 1 plus s into 1 plus s by 10. Okay, so first step is bring standard time constant form. Second step, coming to second step, okay, we have to convert s domain to frequency domain. For that, so we have to put s by j omega wherever s is there. So put j omega. Okay, so g of j omega into h of j omega is equal to 10 into 1 plus j omega by 4 divided by j omega 1 plus j omega into 1 plus j omega 10. Okay, so once you convert s domain to frequency domain, so coming to step 3, so we have to identify how many factors for open loop transfer function. We have 5 factors. Okay, so one is k. Okay, pole at origin. Okay, then we have simple or first order pole. Okay, zero, first order 0, then first order pole. 5 factors. Okay, so constant k 20, sorry 10. Okay, pole at origin 1 by j omega. Okay, for this and this, no corner frequency. First order pole 1 by 1 plus j omega. Okay, so where p1 is equal to 1. Okay, so corner frequency or cutoff frequency is 1 radian per second, reciprocal of this. Okay, reciprocal of this, it is 1 radian per second. Then first order pole, sorry, first order 0, 1 plus j omega by 4. Okay, so z1 is 1 by 4. Okay, so corner frequency is reciprocal of this. Okay, that is 4 radian per second. Then we take uh, another first order pole, that is 1 by 1 plus j omega by 10. The p2 value is equal to 1 by 10. p2 value is equal to 1 by 10. The corner frequency is reciprocal of this. Reciprocal of this. Okay, so we have 10 radian per second. Okay, so once you identify the factors of open loop transfer function, then fourth step, prepare a table factor. Okay, so table factor, in that we have a magnitude curve and phase curve. Okay, for constant k. Okay, constant k, so we have to convert into decibels. For that, so 20 log 10. Okay, so 20 log 10, so this is equal to 20 decibel, whereas phase angle is 0. We already discussed about this. Okay, then one, you take another factor, 1 by s or 1 by j omega. Okay, so there. Okay, so what is the magnitude curve? Okay, so magnitude curve is minus 20 dB per decade. Okay, minus 20 dB per decade. Then phase angle for one pole at origin, that is minus 90 degree. Okay, so coming to another factors. Okay, coming to another factors. Okay, that is 1 by j omega. Okay, take another factors 1 by 1 plus j omega, 1 plus j omega 0 dB per decade for omega is less than 1. Okay, then 20 dB minus 20 dB per decade. Okay, for omega is greater than 1. Okay, then for phase angle, you know that. Okay, so my tan inverse of imaginary part by real part. So this is imaginary part, this is real part, minus tan inverse of, okay, omega by 1. Okay, then take another first order 0 1 plus j omega by per. Then for magnitude curve 0 dB per decade for omega is less than 4 plus 20 dB per decade for omega is greater than 4. Then phase angle minus tan inverse. Okay, so here it is plus tan inverse of omega by 4. Okay, here it is not minus, it is plus. Okay, then I will take this first order pole 1 by 1 plus j omega by 10. Then magnitude curve 0 dB per decade for omega is less than 10 radian per second. Then minus 20 dB per decade for omega is greater than 10. Then phase angle is, the phase angle is plus, minus tan inverse of omega by 10. Okay, then so once you complete that step 4, coming to step 5, prepare the table for magnitude. Okay, so we have to find out the resultant slope for each factor. Okay, then k is 10. So if you convert this into decibel, that is 20 dB. Okay, so 0 dB uh, dB per decade slope. Okay, then you take the simple one pole at origin. It is straight line of slope minus 20 dB per decade. Okay, then start point is point 1. So end point is next corner frequency. Okay, so next corner frequency is 1 radian per second. Then you take this simple 0, uh, uh, simple pole 1 by 1 plus j omega minus 20 dB. That is previous slope is minus 20 dB. For this is minus 20 dB. Minus 20 minus 20, it is minus 40 dB per decade. Okay, so where it start? It is starts at omega value is equal to 1 radian per second, ends at 4 next corner frequency, that is 4 radian per second. Then you take the first order 0 1 plus j omega by 4. Okay, previous slope is minus 40. For this 0 it is plus 20 dB. So minus 40 plus 20, it is minus 20 dB per decade. Where it starts, start point is 4, omega value is equal to 4, end is 10 radian per second. Then to take another first order pole 1 by 1 plus j omega by 10. Okay, previous resultant slope is minus 20 dB. Okay, for this it is minus 20, minus 20 dB minus 10, minus 20 dB, it is minus 40 dB per decade. Okay, start point is 10, end point is infinity. Okay, infinity. Then coming to step number 6, prepare the phase angle equation for given function. Okay, for constant k, okay, phase angle is 0, one pole at origin, the phase angle is minus 90 degree. Then for simple pole or first order pole 1 by 1 plus j omega, This is tan inverse of, okay, imaginary part real by real part. Okay, so imaginary part is omega, real part is 1. Over here, phase angle is equal to minus tan inverse of omega by 10, or omega by 1. Then for first order 0, 1 plus j omega by 4. Okay, phase angle is plus tan inverse of omega by 4. Then for this first order for 1 by 1 plus j omega by 10. So phase angle is minus tan inverse of omega by 10. Then prepare the phase angle table. Okay, so omega. Okay, then one pole at origin, then minus tan inverse of omega, that is 1 first order pole. Okay, then first order 0 plus tan inverse of omega by 4, then minus tan inverse of omega by 10. The resultant summation of these 4. Okay, so omega value is equal to zero point 0.1. Omega value is equal to zero point 0.1. So this will be minus 90. Then if you substitute omega value is equal to zero point 0.1, here it is minus 5.7 degree. Then here it is 1.43 degree. Then if you substitute omega value is equal to zero point 0.1, then the resultant total is minus 94.87. Like that, you have to select the omega value. So corresponding, when you substitute corresponding omega value, so this will be the this one for zero point 0.2 minus 11.3. Then for this, it is 2.86 degree. For here, minus 1.14 degree. Then okay, so resultant summation of these four minus 99.58 degree. Like that, you select the omega value. So this is the resultant, okay, phase angle. Okay, we have tabulated over here. Okay, so once you complete the magnitude table, magnitude resultant table and phase angle table, then we have to go for the constructing the magnitude plot as well as the phase angle plot. Okay, now as we discussed already, x-axis is logarithmic scale, so that is non-linear scale. Okay, so because so omega is frequency is varied from 0 to infinity. Okay, for linear scale it is difficult to accommodate, so that's why we use the logarithmic scale. Okay, then y-axis is linear scale. Okay, if you take the magnitude plot, okay, x-axis is logarithmic scale, it is log omega. Then y-axis, okay, so y-axis is in decibels, magnitude in decibels. Okay, then so initial magnitude you have to consider, you take the 0 degree line. Okay, okay, now you take the 0 degree line, 0 dB line, draw it. Then we have to consider the initial magnitude. So initial magnitude is equal to, so K plus pole or 0 at origin. Here we have a one pole at origin. Okay, so 20 plus 20, that is 40, 40 dB. So this is the initial magnitude. Okay, so initial magnitude, then you consider, okay, so then you consider the uh, 1 by S or one pole at origin. So what is the resultant slope? That is minus 20 dB per decade. Okay, from this point you count downwards. Okay, so this is 20 dB per decade from year to year. Okay, from year to year. Okay, so that is decade. Then take that, draw from that you join this point and this point. Okay, so this point and this point. Okay, that is the that is next. You consider another factor, so that resultant, so resultant slope is minus 40 dB per decade. Okay, so minus 40 from this point, count downwards 40, 20 and 20, 40. Okay, so here then decade. Okay, so we supposed to join from ear to ear, but we have a corner frequency. What is the next corner frequency? That is 4 radian per second. Okay, so we have to, okay, stop from ear to ear. Next corner frequency is, okay, 4 radian per second. Then from this point, okay, so you take the another first order 0. So what is the resultant? That is my minus 40 plus 20, that is minus 20 dB per decade. So from this point, okay, that is 20 dB, count 20 dB downwards per decade from 4 to year 4. Okay, from 4 to 4, then you supposed to join here, but we have a another corner frequency at 10. Okay, so another corner frequency at 10. Okay, so it has to be joined till there. Okay, then you take another first order pole, so the resultant magnitude is 40 dB. Okay, so 40 dB, you take this point, count downwards 40 dB. Okay, okay, then per decade. Okay, per decade it is here. Okay, per decade, then join from this point to this point and extend it simply. Okay, it has to be, okay, extended till infinity. Okay, this is the resultant magnitude. Okay, so now you can see it. Okay, from here to here. Okay, so this is the resultant slope minus 20 dB per decade. Okay, that is one pole at horizon. Then from here to here. Okay, so that is another resultant pole, that value is minus 20 dB per decade. Okay, this is for a first order pole. Then another resultant slope, this is minus 20 dB per decade, that is for first order 0. Okay, then from here to here. Okay, so that is minus 40 dB per decade, that is the for final another fifth factor, that is first order pole. Okay, this is the magnitude. Okay, then now you consider, okay, now we have to draw the, okay, phase angle. Okay, so these are the corresponding frequencies. Okay, so omega value, so this is the resultant resultant phase angle. Okay, now you take this and plot the corresponding value. Okay, now we can here, so these are the location points. Okay, points, points. Okay, locate the points, and these are joined by smooth curve. Okay, so these are joined by the smooth curve. Okay, so these are the joined by smooth curve. Okay, so these are the magnitude plot is right line. Here it is joined by smooth curve. Okay, so omega value corresponding phase angle. Okay, so this is the corresponding phase angle. Now it crosses the minus 180 degree. Okay, now it crosses the minus 190 degree. Okay, now you take this, okay, and project it, okay, till here. Okay, now we have to measure the phase angle as well as the gain margin. Okay, from here to here. Okay, from here to here. So this is the gain margin. Okay, so if you count from here to here, okay, each unit is 4 dB. Okay, so if you count that, total is 92 dB. Okay, now corresponding frequency. Now it is corresponding frequency, that is called as the phase crossover frequency. Phase crossover frequency. Okay, now you take the magnitude plot where it crosses the 0 dB line. It crosses here. Draw the line, vertical line. Okay, so this one. So this frequency is called the uh, gain crossover frequency. Here it is called as the gain crossover frequency. Then phase margin from here to here. Okay, from here to here. So each unit is 6 degree. Okay, so if you count, so total is 32 degree. Okay, sign convention. Okay, sign convention. So this is positive. Gain margin below 0 dB line is positive. Then here phase margin, so this above this line, so this is positive. Okay, so gain margin is 92 plus 92, phase margin is 32 degree. So both are positive. Okay, so both are positive, then the system is said to be stable. In other words, gain crossover frequency. Now this is the gain crossover frequency, so this is the phase crossover frequency. So gain crossover frequency, it is less than phase crossover frequency, hence the system is stable.